So in this video, we're going to introduce the idea of space groups. In another video, we talked about this 32 so-called point groups. And what we're going to do is take a look at how translation affects those 32 point groups. So one of the point groups, for example, is 2 over m, 2 over m, 2 over m. And in another video, we showed how a mirror plane can be converted into a glide plane if we have some translation along some axis. So let's say we have some A, B, and C axes here. And in a normal plane, we might have a tree that's perpendicular to A, and it might be reflected across the A axis, and we would see it over there. But what if instead of directly reflecting it across the A, what if instead we took that reflection and shifted it down along the A direction so that our new tree was over here instead? So that means our motifs would actually be this original one here, and then this one over here, and this is just kind of a makeshift to show the progress. So we'd reflect the tree and then translate it. We call that a glide plane. We have a separate video on that. So what would happen? Well, we have different kinds of glides. We have an A glide if the movement is along the A direction like we've just shown, or a B or a C or a diagonal glide or a diamond glide. Actually, diagonal is shown as an N. We use D for diamond. So from the 2mm, we can have something like 2 over n, 2 over n, 2 over n. So instead of having mirrors that are perpendicular to the twofold axes, we can have diagonal glides that are perpendicular to those twofold axes. And then we can have a 2 over b, 2 over a, 2 over n. So we still have a diagonal glide in that third position, but here we have an a glide and a b glide that are replacing the mirrors in this point group. Or we could have a 2 sub 1 where we have a screw axis. That could be perpendicular to a mirror, and then we could have a regular twofold perpendicular to a mirror. That's a 2 sub 1 over there, and then put an A glide in that last point. Remember, with the 2 sub 1, that is a twofold axis where the translation distance is 1 over 2, where the subscript becomes the numerator and that base becomes the denominator. So all of these, all three of those are related to this point group 2 over m, 2 over m. What we've done is taken the point group and we've added some translation. And so we can play these games, and from 32 point groups, we can get 230 space group total. So that 230 space group symbols represent all the possible ways that we can add translation, a combination of glide planes and screw axes, to things like point groups, plus an additional variation. In another video where we talk about Bravais lattices in the unit cell, we have unit cells that can be described in a couple of different ways. So for this case here, where we have just atoms at the corners, we would call that primitive, and conveniently enough, we refer that to that as the letter P. We can have the same box with atoms at the corners, but we could put an atom in the center, and that would be body-centered, and that would get the letter I. A little bit inconvenient, but we're going to use B for something else. Remember, here we still have atoms at the corners. Then we can have atoms not just at the corners, but also at the faces. So let's draw a little cube here. But now what we're going to do is have an atom that is on the face. So let's say we have one on the left face and the right face, the top face and the bottom, and then the one in front, and then the one in back. So this would be, conveniently enough, referred to as an F for face-centered. So why don't we use the B for body-centered? Because instead of having atoms on all of the faces, we can instead play another kind of game where we have atoms on the corners like we would in a primitive cell. But what we'll do is we'll have atoms that are not on all of the faces, but maybe just along the B-axis. So if the B-axis is left to right, we can put a pair of atoms there. So there's our B-axis. The B-axis would be this left to right direction. This would be A, and this would be C. So the A, B, and C directions. So if we have atoms on the B faces, positive B and minus B, then that would be something that we would refer to as a B-centered unit cell. So we have all these designations. Let's take a look at some point group symbols. So you can have let's say P 2 sub 1, that can have maybe B glide perpendicular to it, a 2 sub 1 with an A glide perpendicular, and then just a regular 2 over M. So this is something with a primitive unit cell, just atoms at the corners, nothing fancy going on there, as we've already drawn in a previous part of the chalkboard. Then we have a twofold axis that has been replaced by a screw axis, a 2 sub 1, and another twofold replaced by a screw axis, a B glide and A glide, and then this is supposed to be an M, just a regular 2 over M. What point group would this relate to? Well, if we take out all of the translation, we would just have the B glide turn into a mirror, the screw axis would turn into a regular axis, same over here, the screw becomes a regular axis, the A glide becomes a mirror, and then this one has no changes to it. We just have 2 over M, 2 over M, 2 over M. And we would say this is isogonal. That is Greek for equal angles with respect to all the other examples we showed that are also related to 2 over M, 2 over M, 2 over M. Let's take a look at it. Just a couple more examples before we go. We can have in the triclinic group just 2 space groups. There's not a lot of symmetry in the triclinic system, so we can have a P1 or a P bar 1. This fellow would devolve into the point group of 1, and this would devolve into the point group bar 1. And let's take something a little bit more interesting than that. Just as our last example, let's say we had an I 4 sub 1 over A, bar 3, and then a 2 over D. So what point group would this be related to? So the I is the body-centered case for the unit cell. We'd just drop that. The 4 sub 1 is a fourfold rotational axis with a screw axis, translation distance of 1/4. Get rid of that translation distance, and we just have a regular 4. That would be perpendicular here to an A glide, but that would devolve into a mirror. Here's a bar 3, nothing special going on there. D for a diamond glide, so that diamond glide becomes a mirror plane, and so this becomes an example of the point group 4 over M, bar 3, 2 over M. So you could take a look at the various 230 space groups. We've looked at a couple of examples. They are these things here. When you see a capital letter in front of a point group looking symbol, you're looking at a space group symbol. There are 230 possibilities that are consistent with the various crystal systems that we've discussed in other videos. And this is a kind of a starter on what these kinds of symbols mean.